Hi everybody, today we're going to talk about acid-base equilibria. This is the last part of chapter 19, acids and bases. So we had talked about strong and weak acids and bases and the difference between them. So a strong acid or base is one that ionizes or dissociates 100% to completion. A weak acid or base is one that only partially ionizes, so it doesn't go 100%. So HA is our generic acid here. There is no such thing as HA. This is just the generic example. And it partially dissociates into H plus and A minus. So we said typically a little bit of H plus and A minus are produced, but the majority of it remains as molecular HA. If I wanted to write the KEQ expression, the equilibrium constant expression for this, I would do products over reactants, raised to the power of their coefficients. So let's do that. So it would be the concentration of H plus times the concentration of A minus over the concentration of HA. So haha. So this is KQ, or K, the equilibrium expression for this process right here. Because this is not just any process, this is a special type of process, the dissociation of an acid. We call it, instead of just KEQ, we call it KA. So A stands for acid, and Ka is the acid dissociation or ionization constant. Acid dissociation or ionization constant. You don't have to say this whole thing. You can say acid dissociation constant or acid ionization constant. Similarly, a weak base, BOH, again, this is not boron, this is just the generic example of a base, that partially dissociates into B plus and OH minus, so a little bit of B plus and a little bit of OH minus are produced, but the majority of it remains as BOH. If I wanted to write the KEQ expression for this, again, I'd write products over reactants raised to the power of its coefficients. So concentration of B plus times the concentration of the OH minus over the concentration of the BOH. So BOBO. And because this is a special process, we give it a special name. So the B stands for base. And so this is the base dissociation constant, or the base ionization constant. Now, it turns out that if you take Ka of an acid times Kb of its conjugate base, you multiply them together, you get Kw, which is the water ionization constant. Or if you take Kb of a weak base times Ka of its conjugate acid, again you get Kw, which is the water ionization constant, which we know is 1 times 10 to the negative 14th. So what does that mean? What does Ka and Kb mean? Well, Ka, again, is the acid ionization constant. It's products over reactants, just like any K, right? So what if my Ka was really high? What does that tell us? Well, in general, if K is really high, that means it's very product favored, right? The higher the K value, the more product favored it is. If K is really small, that means it's reactant favored. So the higher the Ka, that means the more ions I get, and so the more ionization, or the stronger the acid. So the higher the Ka value, the stronger the acid. The lower the Ka, the weaker the acid. I'm going to go ahead and write that down. The higher Ka, the stronger the acid. And what does acid strength mean? It means strong, the percent ionization. So the higher the Ka, the higher the percent ionization, the more ions I get, which means the more H pluses I get, which means the lower the pH, the more acidic it is. Similarly, Kb, again, if it's high, that means I get a lot of ions, which tells me that it's a stronger base. So the higher the Kb value, the stronger the base, meaning that I get more ionization, more OH minuses, and a higher pH. So let's write that down. The higher Kb, the stronger the base. So I can give you two acids with their Ka values and tell you which one is stronger, or similarly two bases with their Kbs and ask you which one is stronger. So looking back at this equation, if I take an acid, find its Ka, times its conjugate base, find its Kb, and multiply them together, you get Kw. So Kw is a constant. It's always 1 times 10 to the negative 14 at room temperature. So that means that the stronger the acid, the weaker its conjugate base. Because if I multiply two numbers and get a constant, then if I increase one of them, I decrease the other. So the stronger the acid, the weaker its conjugate base. And vice versa, the weaker the acid, the stronger its conjugate base. Or if I'm talking about a base, the stronger the acid, the base, the weaker its conjugate acid, or the weaker the base, the stronger its conjugate acid. So let's look at the type of problem that I would give you dealing with Ka or Kb. So number 1 says acetic acid is a weak monoprotic acid. This is the main ingredient in vinegar. Our commercial vinegar that we use at home is 3% acetic acid. If the initial concentration of acetic acid is 0.2 molar and the equilibrium concentration of the H3O plus ions is 0.0019 molar, calculate Ka for acetic acid. So the first thing you want to do, if you're talking about an acid or a base, and it's especially weak, whether it's strong or weak really, but especially if it's weak, you want to write the dissociation equation or the ionization equation for it. So when you put it in water, what happens? So I know that acetic acid is CH3COH. And you can either add it to water or just do the arrow right away. It dissociates into H plus and CH3COO minus. This is the acetate ion. If you prefer, you could write the acetic acid plus water. You'd still get the acetate, but this would be H3O plus, which is the same thing as H plus and water, right? So H plus and H3O plus are synonymous. So after you write the dissociation equation, then you write the Ka expression, since we're asked for Ka. And so my Ka expression is equal to concentration of the H plus times the concentration of the acetate ion over the concentration of the CH3COH. Now, I do want to show you also that, let's say in this equation or in this problem, you don't know what acetic acid is. They don't give you what the formula is. No problem. As long as they tell you that it's a weak monoprotic acid, if you write it as HA, that is totally fine. You can write it as this and write the Ka expression as the concentration of H plus times the concentration of A minus over the concentration of HA. Either one, it works. So don't worry about, figuring out how to write the equation if you're not given what the formula is. Then you can just write it as this. If you know, then that's great. Okay, so now it asks me to calculate the value of Ka, right? And so all I need to do is just plug in the concentrations here. So the concentration of H plus at equilibrium, that it gives me, it's 0.0019 molar, so I got this number, right? And again, H3O plus, H plus, they're the same thing. Proton or hydronium or hydrogen ions are all the same thing, right? So I have this number, that's great. It doesn't really mention anything about the acetate ion anywhere. And for the acetic acid, it does give me a concentration, but I can't use that concentration. Anybody know why? The reason is, remember when I write K, the equilibrium constant, to find it I need to plug in the equilibrium concentrations, right? The concentrations when I reach equilibrium. Well, is this an equilibrium concentration? No, it tells me that's the initial concentration. So this is telling me that I start out with 0.2 molar. Some of this gets used up and turns into H plus and acetate, and the rest of it remains as acetic acid, right? So some of the 0.2 molar is used up. So when I reach equilibrium, this number is not going to be 0.2 molar. It's going to be less than that, but I don't know how much. And so I can't really use that right away. So here's what you do. You do something called an ice chart or a rice chart. So I'm going to go ahead and do that. So what you do is you write your equation. I'm going to rewrite it down here. So move this a little bit. And I'll rewrite this equation here for myself. Again, you can write the HA equation that works as well. And you do something called rice or ice. So you write ice, or you can write rice. R stands for the reaction. So R is the reaction. I is initial. C is change. And E is equilibrium. So what you do then is you fill out your chart. So let's start with initial. So initially, I am told that my acetic acid is 0.2 molar. So the acid is 0.2 molar. So I can fill that up into my rice chart, 0.200 molar. Great. How about my H plus and acetate? Well, initially, at the very beginning, before the reaction takes place, I have reactants. I don't have any products, right? At the very beginning of the reaction, initially, I only have reactants. I have no products. So my products are zeros, right? Because they're products. Next, I am not told anything about the change anywhere here, but the only other number I'm given is that the equilibrium concentration of the H3O plus is 0.0019 molar. So where does that go? Well, it says equilibrium concentration, so that goes under equilibrium. And H3O plus is the H plus, so I put this here. 0.0019 molar. Well, if I know now the initial, and I know what it is at equilibrium, I can figure out what the change is. So if it started out at 0, and it changed somehow, and at equilibrium now I end up with 0.0019 molar, then that means the change that occurred is that it formed 0.0019 molar, right? I can relate the change of all of these based on the molar ratio, right? Because every time I use up one of these, I form one of these, and I form one of these. So if I'm forming 0.0019 molar of this, that means that I'm also forming 0.0019 molar of this. And that means that I'm using up 0.0019 molar of this because it's a 1-to-1-to-1 ratio. So because I'm using it up as opposed to forming, this would be minus 0.0019 molar. So once you're able to find the change for one of them, you can find the change for all of them based on the molar ratios. And in this case, it's a 1-to-1-to-1 ratio. So what I can do now is I can go ahead and plug in my equilibrium concentrations. So to figure out the equilibrium concentration, you add these together. So I start at 0, I gained 0.0019, so I end up with 0.0019 molar. For this one, I started out as 0.2 molar, and I use up 0.0019 molar, and so at the end, I end up with 0.1981 molar. So now that I have the equilibrium concentrations, those are the ones that I can plug into my Ka expression. So back to my Ka expression, I plug in my equilibrium concentration. So at equilibrium, my H plus is 0.0019. My acetate is also 0.0019. And my acid is 0.1981. And I just punch that into my calculator and find the answer. And if you plug that in, you get 1.8 times 10 to the negative 5th. And that is the answer. That's the value for the Ka. Let's look at another problem. So this one says ammonia is a weak base. If the initial concentration of ammonia is given to us and the equilibrium concentration of the hydroxide ion is given to us, calculate Kb for ammonia and also calculate Ka. So if you know the equation, you can go ahead and write it out. If you don't, you can write the generic equation. So I'll write both. You pick whichever one you want. So ammonia is NH3. When I put that in water, I get NH4 plus and OH minus. Now, if you don't like that, you could do the generic equation, so BOH plus water. Or, yeah, I guess you don't need to do the plus water. You can, but you don't have to. B plus and OH minus. Either one. Then you write your Kb expression. If I'm here, I would write my Kb expression as, I'm actually going to write it on the bottom here so that I have some room for my rice chart. So my Kb expression is going to be the concentration of the NH4 plus times the concentration of the OH minus over the concentration of the NH3. Remember, we don't put the water in because it's a liquid. If you were doing it with the BOH, the generic one, you would write your Kb expression as the concentration of the B plus times the concentration of the OH minus over the concentration of the BOH. Again, you don't need to write both. You pick whichever method you prefer. Then you try to plug in your numbers. You are given the equilibrium concentration of the hydroxide. It's right here. But you're not given the ammonium. You're also not given the ammonia because the ammonia, this is an initial concentration. So when you're given the initial concentration, you're trying to find the equilibrium concentration, you do a rice chart. So I'm going to go ahead and do a rice chart. So remember, I stands for initial, C stands for change, E stands for equilibrium. And I'm going to go ahead and fill it up with what I know. And so I know that ammonia's initial concentration is 0.150 molar. Don't care about the water because it's a liquid. I know that the ammonium and the hydroxides are zeros because these are products. So at the beginning of a reaction, you have no products. The only other number I know is this number right here, which is the equilibrium concentration. So it goes under the E. And it's for the hydroxide, so it goes right here. So I'm going to go ahead and plug that in. This is 1.6 times 10 to the negative third molar. And since I know the initial and the equilibrium for the hydroxide, I can figure out what the change is. And so the change is that it formed 1.6 times 10 to the negative third. Again, you can do this with this reaction or with this reaction. It does not really matter at all. If you find the change for one of them, you should be able to find the change for all of them based on the molar ratio, because for every one of these that gets used up, you form one of these and one of these. So if you formed 1.6 times 10 to the negative third of this, then you also form 1.6 times 10 to the negative third of this. And you use up 1.6 times 10 to the negative third of this one. So at equilibrium, you just add this plus this and this plus this to get your equilibrium concentrations. So for this one, you get 0.1484 molar. For this one, you get 1.6 times 10 to the negative third molar. Now that I have my equilibrium concentrations, I can plug these in to my Kb expression, because this is always at equilibrium. So my values would be 1.6 times 10 to the negative third times 1.6 times 10 to the negative third divided by 0.1484. And you get 1.7 times 10 to the negative fifth is your answer. That is your Kb for ammonia. Now it also asks you to calculate Ka. Well, Ka for what? Well, if they give you a base and they ask for Ka, that means they want Ka for its conjugate acid. And so ammonia is a base. What is its conjugate acid? It is ammonium. So ammonium ion, what is the Ka for ammonium ion? If you were doing the generic one, then you'd find Kb for the BOH, that's the base. You'd find Ka for its conjugate acid. So how do I do that? You use the equation Ka times Kb is equal to Kw. So let's do that. Write it down here. So Ka times Kb is equal to Kw. This works for an acid and its conjugate or a base and its conjugate. So I'm looking for Ka. I don't know what that is. I do know what my Kb is 1.7 times 10 to the negative fifth. And Kw is 1.0 times 10 to the negative 14. And so I take 1.0 times 10 to the negative 14 divided by 1.7 times 10 to the negative fifth. I end up with Ka for the ammonium ion being 5.9 times 10 to the negative 10th. And that's my answer. Now, real quick, what if... interesting. What if this question here asked you, instead of asking for Kb for ammonia, what if it just asked for you to calculate Ka? How would you do it differently? You would not do it differently. You would do it exactly the same way, because if they give you ammonia and they say that's a base, you have to find Kb first. You write the dissociation for the base, find the Kb, and once you find the Kb, then you find the Ka. So you would have done it exactly the same method. So watch out if you're given an acid or a base, because that would depend if you're looking at hydroxide or H+. Also, watch out if you're asked for Ka or Kb. Hope this helps, and this is it for the notes for this chapter. I hope you have a wonderful rest of your day.